this is completely different from Monday. There's no similarity between today and Monday. All right, so how many people have ever worked with matrices before? Okay, that's a lot of hands. Let me ask the more pointed question. How many people have never worked with matrices? Be honest. Great, okay. These two people. All right, taught them. The people who just raised their hand, have you seen matrices before? Have you actually seen other people work with them or done anything like that? Or is it?
I've seen them, but don't remember a spot.
Okay, all right.
That's a fair summation.
That's fair summation for a lot of this.
Matrix is giving me
All right, so we're going to go through. We're going to sort of review basic properties anyway. So usually have the most to learn here.
Yay.
Good. Yeah. All right. So general properties of matrices, matrix arithmetic, properties of square matrices. So lots of stuff involving square matrices that doesn't apply to other matrices. And then we'll use matrices to do systems of linear equations, including Cramer's rule. And it's not listed in here, but we'll talk a little bit about eigenvalues. Oh, it is listed there. Okay. All right. So what is a matrix? A matrix is just some rectangular array of quantities. So it's usually written like this as a two-dimensional table, put with brackets or parentheses surrounding it. And every entry here is a number. Okay, usually a number. It's some quantity. And if I have a matrix capital A, if we want to name each entry of the matrix, there's a standard way of doing that. Every letter here has two indices underneath. So that's not 11, 12, and 13. That's 1, 1, 1, 2, 1, 3, up to 1n. 2, 1, 2, 1, 2, 2, 2, 3, and so forth. The first number says what row the entry is in, and the second number says what column it's in. The rows are horizontal. That's row 1, row 2, row 3, and so forth. The columns are vertical. That's column 1, column 2, column 3. So every entry, the indices, just indicate what row it's in and what column it's in. The dimensions of the matrix are the number of rows times the number of columns. So this matrix is m by n. It has m rows, so count 1, 2, 3 down to m, and it has n columns, 1, 2, 3 up to n. So we say that this matrix is m by n. So rows always come first. The number of rows, then the number of columns. Rows, columns, don't say column, row, just say row, column. Okay. The elements of the matrix, the entries of the matrix, are these numbers. These numbers are also called scalars. And we have a number for each row and each column. We have each row from 1 to m, and from each column from 1 to n. There's some number, some unique entry in that position, denoted by A, ij, or ith row and jth column. Matrices are used all over the place. There are so many uses of matrices. There's just too many to mention here. We'll scratch the surface of this just barely in today's class. But we have more concepts to talk about. So in any matrix, the main diagonal of the matrix is the elements of the form AII. So the row number and column number are the same. That's going to be starting in the upper left-hand corner and just going down diagonally to the right. So that's A11, A22, A33. That's called the main diagonal of the matrix. And here, if the matrix is square, a square matrix is the same number of rows as columns, then the main diagonal goes all the way down to the lower right. But if the matrix is not square, so the number of rows and columns are different, then this main diagonal won't it'll just hit one of the edges first before it doesn't actually hit the bottom right element. Okay, it always starts at the top left though. Always. Okay. Some examples of an example of a matrix. If a matrix only has one row, we call it a row vector. If a matrix has only one column, we call it a column vector. So these are both matrices. We call them vectors, but they're actually, a vector is just, for our purposes, a vector is just a special kind of matrix. One with only one row or one column. A null matrix, also called a zero matrix, is one where all the entries are zero. So here's a zero matrix right here. So all the entries are just zero. Okay, and it could be of any dimension. A square matrix, well, I said what a square matrix was. A square matrix is one where the two dimensions are equal. So here's a 3 by 3 matrix. And here's an actual concrete example where we actually plug in numbers. So 3, 2, 1, 2 minus 6, 1. That's a square 3 by 3 matrix. We say that the size of the matrix, in this case 3, is the order of the matrix. Say that too. So this is a square matrix of order 3. That's the common number of rows and columns. All right, so that's basically what a matrix is. But really, we get into more meat when we talk about things to do with matrices. What can you do with a matrix? So the easiest thing you can do with a matrix really is take its transpose. So the transpose of a matrix is obtained by you interchange the rows and columns. So the ijth entry of A transpose, so we write the transpose of the matrix A, we write it like this. We write a superscript T. The ijth entry of the transpose is the jith entry of A. Another way of saying that, if the ijth entry of A is Aij, then the ijth entry of the transpose is Aji. So you switch the row and the column. So here's a matrix A. Here's its transpose. Notice what we did. If you read off the first row of A, that becomes the first column of the transpose. And similarly, the first column of A becomes the first row of the transpose. And similarly for the other rows and columns. So in a transpose matrix, another way of thinking it is you are just you're reflecting the elements across the main diagonal. So this 2 gets swapped with this minus 2, and this 1 gets swapped with a 0, and this 1 gets swapped with the minus 4. Okay, and the main diagonal elements stay put; they're not moved. But if I give you a matrix and I ask for the transpose, the easiest thing to do is like read off row by row and write those numbers in column by column in the transpose. That's the easiest way to give me a transpose. Okay. So any matrix can be transposed, even a square one, even a non-square one. So here is, what are the dimensions of that matrix? 3 by 4?
4 by 3, your rows and columns?
Yeah, exactly. It is not 3 by 4, it is 4 by 3. The left-hand side matrix, okay, forget the transpose. That matrix there is 4 by 3. Because you count the number of rows first. It has 4 rows, 3 columns. So that's 4 by 3. But now when you take its transpose, you get a 3 by 4. So taking the transpose of a non-square matrix swaps the dimensions as well, right? If you only have 4 rows here, you're going to have 4 columns there. Okay, so you can take the transpose of a non-square matrix. In that case, you'll get a matrix with different dimensions. The dimensions are swapped. Here's another example. Ignoring the T here, what's the dimension of that? 2 by 3. 3 by 2. All right. So note, easy enough. if you take a matrix and you transpose it twice, you get back the same matrix. Pretty not hard to see, right? Okay. All right, so let's do some matrix arithmetic now. You could take a matrix and multiply it by a number, k. General, when we talk about vectors and matrices, if we just want to talk about a single number, we call that a scalar. So keep that in mind. A scalar just refers to a single number. So we can multiply matrix A by a scalar k, and it gives us a new matrix denoted like this: k times A or A times k. It doesn't matter. And all you do is you take every entry of A and multiply it by k. Just do that everywhere, and you form the matrix of the results. So if I multiply this A by a half, I just take a half and multiply each entry in A by a half and put the corresponding entry down there. So 10 becomes a 5, minus 20 becomes a minus 10, and so forth. Notice you can write 1/2 A. You could also write that as A over 2, like you would pretend A is a scalar. You could write 1/2 A as A over 2. You do the same thing with a matrix. Okay. So scalar multiplication also includes scalar division. You can divide by a scalar, and it's just multiplying by 1 over the scalar. All right. Matrix addition and subtraction. So, just like with scalar multiplication, you can add two matrices with the same dimensions, and it's just done entry-wise or component-wise. So you add the corresponding entries of one matrix, the entries of one matrix with the corresponding entries of the other. So here A and B are two matrices. What are the dimensions of A and B? Here? 2 by 3. Good. And notice the sum is also going to be 2 by 3. And each entry in the sum is just the sum of the corresponding entries in A and B. So for the top row, left column, 4 plus 3 is 7. 3 plus 2 is 5. Minus 2 plus 6 is 4, and so forth. Okay. So scalar multiplication is easy. Matrix addition is easy. Okay, it's just you're just doing it for every entry. So addition is commutative and associative for matrices, just like it is with scalars, because really that's all you're doing. You're just adding scalars inside the matrices anyway. So what that means, commutative, what does that mean? Commutative. Remember? Yeah, A plus B is equal to B plus A. You can swap the order, it doesn't matter. Associative, what does that mean?
So if it's A plus B plus C, it's A plus B first, or you can do B plus C first.
Yeah, so if I add three matrices together, the order in which I add them doesn't matter. So I could add A and B first, and then take that and add that to C. Or I could add B and C together first, and then take that and add that to A. And what associativity means is that you could write the sum of three or more matrices without parentheses, because it doesn't matter how you group them, you're going to get the same answer anyway. So, all right. So that's associative. So this is true of scalars. So it's going to be true of matrices because we're just adding this thing. All right. Dimensional conformance. So if we go back, notice A and B had the same dimensions. If A and B have different dimensions, then there are going to be some entries in one matrix that don't correspond to anything in the other matrix. In that case, we say that the matrices are non-conformant, and in which case the sum or the difference of the matrices is undefined. So, in order for the sum and the difference to be well defined, A and B have to have the same dimension. Oh, I didn't mention A minus B. What do you think A minus B does? Yeah, it's just, again, it's component-wise. You take an entry in A and subtract the same entry in B, and that gives you the entry in C. But both of these, in order for this to be well-defined, A and B have to have the same dimension. So we don't even try to do it if A and B have different dimensions. So here's some general laws, which I've mentioned. So this one is the commutative law. This one's the associative law. If I take a matrix, if I negate a matrix, that's the same thing as just multiplying it by the scalar minus 1. And what that does is it just negates every entry in the matrix. Distributive law, if I take a scalar multiple of a sum or a difference of two matrices, then I get the sum or the difference of the scalar multiple of each one. So you can distribute scalar multiplication across matrix addition or matrix subtraction, okay, just like you can with ordinary numbers. If you take the transpose of the sum or difference, you get the sum or difference of the transpose. Okay, you're just moving the entries around to a different position, but you're still adding the same entries together. So those are pretty basic. So that's commutative, associative, negation, distributive law for scalar multiplication, and the transpose. All right, basic properties. These are properties, if you work with matrices a lot, you use these properties repeatedly, and after a while you just use them without even knowing it. Okay, it's like water to a fish. Okay, it's just you just use them as a matter of course, and you may not even be aware you're using them. Okay. Matrix product. So now we get to something interesting. So you multiply two matrices together. It's not like you just multiply corresponding entries. This is a little more complicated. So matrix multiplication, this is what really makes matrices interesting, I think. Otherwise, you're just taking bunches of scalars and doing something simultaneously on lots of stuff. So matrix product is defined as follows. If C is, if you have two matrices A and B, and the entries of A are given by these numbers, A, I, K, where I is the row number and K is the column number, and the entries of B are given by B, K, J, where again K is the row number and J is the column number, then the entries of C, the entry in the ith row and jth column of C, here's what you do to get it. You take the ith row of A and the jth column of B, and you multiply the corresponding entries together. So A's over here, B's over here. Take the ith row of A and the jth column of B, and you multiply the corresponding entries. So K is running through the columns of A and the rows of B. You multiply them together, and then you add it all up. I call this the two-fingered rule, because when you do it on a board, it's easy to do it with two fingers. But we'll see an example of this. The dimensional conformance is not the same as for addition. In order for this sum to make sense, the number of columns of A have to equal the number of rows of B. So if A is m by s, B is s by n, that's the number of columns. It has to equal the number of rows of B. That's the number of columns of A. It has to equal the number of rows of B. In this case, they're both s. If that's the case, then the dimensions of C are m by n. So here's one way to remember that. If these are the dimensions, the inner dimensions have to match. If they don't match, it's undefined. But if the inner dimensions do match, then they kind of cancel, and you just take the outer dimensions. Right? So m by s times s by n becomes m by n. And this is true not just for two matrices. If you multiply any number of matrices together, like m by S, S by T, T by N, say 3 matrices, all the inner dimensions have to match. Those match, and they cancel, and you're left with M by N, the outer dimensions. That happens for the product of any number of matrices. You have to have those inner dimensions have to match everywhere. And then they all kind of cancel out. And you're just left with the outer one. All right. So let's do an example how this works, because this is not as easy as matrix addition. So here are 2 matrices, A and B. What are the dimensions of A? 3 by 3. Good. And what are the dimensions of B? 3 by 2. So the point is A has 3 columns and B has 3 rows. So they have the same. So the inner dimensions conform. They match. So we can actually multiply these together. All right. So here's how we do it. To get the first row, first column entry of the product, you take the first row of A and the first column of B. So they have the same number of elements, right? Because this has 3 and that has 3 because of conformance. So here's what you do. You take the corresponding entries. Here's the 2-fingered rule. You take the corresponding entries, multiply them together, and add up the results. So first you multiply 3 times 4, which is 12. You add that to 2 times 2, which is 4, so you get 16, plus 1 times 0, which is 0. So that gives you the 16. All right. So that gives you the 16. Now if we want to find, let's say, this one, this is in the second row, first column. So we take the second row of A and the first column of B. So the row is always in the left factor, and the column is always in the right factor. Do the same thing. Negative 2 times 4 is what? Negative 8. And then what's the next product? 5 times 2 is 10. Good. And 1 times 0 is 0. So it's going to be negative 8 plus 10. That gives a positive 2. So now the row is the third row, first column. So 0 times 4 is 0. Negative 4 times 2 is negative 8. And 3 times 0 is 0. So that's negative 8. Add in all. Okay. That's how multiplication works. So now, first row, second column of the product, I take the first row of A and the second column of B. 2-fingered rule, what do I get? It's going to be 9 plus 12 plus 4, which is what? Second column, second row. Sorry, second row, second column, second row of A, second column of B. What do I get? Negative 6 plus 30 plus 4, that's 28. Okay, and then finally, third row of A, second column of B, 0, negative 24, positive 12, gives you a negative 12. So that's how you define the product. So this is 3 by 3, that's 3 by 2. So the outer dimensions are 3 and 2, so this is going to be 3 by 2. And here is the typical calculations explicitly as we do this in the slide. Questions on multiplication? All right. So basic laws of matrix multiplication. Multiplication is not commutative in general. So it is not the case that AB is always equal to BA. Sometimes it is, sometimes it isn't. If it is, we say that A and B commute with each other. But very often, these two, you get different matrices. If you multiply A times B, you get something different if you multiply B times A. In fact, it's possible that one of these is conformant and the other one is not. So one of these might be well-defined and the other one is not well-defined. That's also possible. However, it does happen to be associative. So it turns out you can multiply a string of matrices together. It doesn't matter how you group them. Like I could group A, B first, or group B, C first. So this is not commutative, but it is associative. What that means is grouping doesn't matter as long as you keep the factors in the same order. Right? You can't rearrange the factors, but you can group them how you want. All right. What else can you say? If I take one of the factors and multiply it by a scalar, I can pull that scalar out of the product. And it doesn't matter which factor I multiply the scalar in. If I multiply it into A or if I multiply it into B, in either case, I get the same answer, and the answer I get by first multiplying A times B and then multiplying everything by a scalar. The reason is when you go through and you look at how you're multiplying these things up, if you've got a scalar multiplying one matrix, that scalar will just factor out of all the calculations. Okay. So every entry of the matrix product will have that scalar factor in it. So you can factor it out. Multiplication actually distributes over matrix addition and subtraction. So, for example, A times the quantity B plus C is AB plus AC. That's kind of nice. And notice, but I need two rules here because it's not commutative. So I also have to say B plus C, that quantity times A on the right, is equal to BA plus CA. Notice that the place where A is being multiplied has to be the same on both sides. Here, you're multiplying A on the left. Here, in each case, you're multiplying A on the left. That has to be true. Here, you're multiplying A on the right. So if you multiply A on the right on both sides. Okay, so you keep the order through the distribution. Okay, here's a funky one. If you take a product, A times B, and take its transpose, it's the product of the transposes, but the order is swapped. You do the B first and then the A. Won't bother proving any of these, but do a few examples of these. You'll see immediately why this has to be true. Okay. Or you eventually see why this has to be true. All right. Questions about matrix multiplication? All right. So I'll typically, I'll give you two matrices with, actual entries, numbers, and I'll ask you to find the product. You can certainly do that for me, right? And I might actually give you some questions that use these laws somehow. Now, you can always just do things out brute force, but sometimes these laws give you a shortcut on computing and allow you to avoid some complicated or redundant calculations. So that's why they're useful. All right, square matrices.
Oh, sure.
Yes, question.
Break time.
Break time. Ah, thank you. All right. Indeed it is. Let's take 10. Good call. And I will turn the internet on for you.
He's trying to learn.
That is exactly what he's trying to do.
When you get like an 8x8.
Yeah, usually I call crime.
So when you're talking about the transpose
Yeah.
for AB and then they switch order, did you take the transpose of B first and then the transpose of A in that example? The previous one?
So right down here?
Yeah, so you have AB and then transpose. So you take the transpose of B first, correct? And then
Well, yeah. You're going to take the transpose of B on the left.
Yeah, right. Because then it'll be either
Yeah.
quarter, like maybe the
And the transpose of A on the right. So, I mean, which one you do chronologically doesn't matter as long as you put them in the right position. Yeah.
It's a joke. I will spend $1,000.
I think I got it. It's been, like, I remembered all the other stuff, but then this kind of like,
That was a little weird. Okay, all
I
right.
was like a little weird now.
It's like curveball. Oh, don't forget. Well, I'll skip these actually. Those would be actually. Oh no, that is several pages. I can see it.
I'm sorry, she drive like 5 miles to get it there. If she one of her points like following kind of make sure you don't off it really flat. Then they build it up and you're drive home. So the next day they're supposed to hang out for that. Like I've already I went there right to work. And then after a while however, somebody drove on a cracks all on the inside. So I get the total like this, right? The expression. I kind of get like the base. Is this the base? Fringe. It starts to get little. It's like you start to get down here. You can group it up. Like that. Wait, I'm trying to find out. Not being fine for the shows like in Germany.
He's like, how do you guys not get this? I used to do it 80 by 80s.
I came up with like a more systematic approach on the work for everybody, but like when you get to the section, you got to figure out, that that's not what we did when we had the question. The question is X and your X is there was some eliminating factor like this. It can't be less than
what was the
we did that for
password for the computer? Oh, no, I'm sorry. That might help.
We're back there just so I could have it.
And write it on the board. Same thing is shift key down to page 24. Page 24, TSEC 0000.
Ah, okay.
I'll write that on the board.
The username is
Still same.
Ah, okay. Thank you.
Yes. Got it in there. Here's a laptop password and login.
In your head, you're like, that's my brain doing that.
Just 4 zeros, same thing, but 4 zeros on the end. Same thing as on the end. Okay.
We can plug those in here.
Last night I tried letter to get because of
Oh, yeah.
Yeah. Yeah.
Did we miss it?
This is the best thing about doing that. Like,
At least you know what you should be doing.
yeah, it's a way to check it. Exactly. You've got time.
Who got it?
Like skill, outside my yoga, can't eat nothing. I'm like anorexic and I'm going up after day.
Did you know that this 12 cups, a cup is 4 ounces, 6 ounces? It might be, I think you're right. Call it a cup different. Oh, yeah, first that's very good. You know, they think the Enlightenment was in part caused by the combination of coffee and tea. Speaking of drinking alcohol.
Should you stop drinking good stuff and waste it all?
That and shrooms.
Yeah. Oh no, of course.
Yeah. Okay. I don't see how we get that yet. You know, maybe.
Yeah.
I did a lot of self-study on matrices. In back in the spring. Khan Academy videos and matrices are awesome. The best ones he does.
So, but then I was going to last night. Apparently, forgot most of what our view. So, I didn't get all the way to the track.
It's rough reading that. I'm much better at watching the lecture.
It is easier to pick up on his back with some of the people who have the slides. If you go to the book, they present everything with that whole, series.
Math language.
Head start circumstance, some
I don't know anybody, save for mathematicians, that look at that. Yeah. Oh, okay, I get it.
Oh, you mean the mathematics speak? They
Yeah,
always
math.
put laws in.
All right, let's start again. All right, so we're back. Square matrices. So a square matrix is one where the number of rows equals the number of columns. I've already said that many times. And there are lots of properties and rules that apply to square matrices that don't apply to non-square matrices. So we're going to talk about some of them then. So square matrices are in some sense very special. They have lots of rich structure that you don't get with non-square matrices. So one of the most important quantities associated with a square matrix is called its determinant. Determinants, it's a scalar, and it is derived from the values, the scalar values, the entries of the matrix along with their positions. And we usually write, if A is this matrix like this, we usually write the determinant of A. We use the absolute value symbols, the vertical lines, or we call it det of A, determinant of A. Sometimes it's also called delta. And notice here we're also using the vertical line, so I don't have parentheses delimiting the entries here. I have actual vertical lines. So this represents the determinant. This is important. This is a scalar. It is a scalar that is derived from the matrix. It's calculated from the matrix in a certain way. Why is the determinant useful? It's useful for a number of things. Our chief use for it is going to be we're going to compute the multiplicative inverse of a matrix. And we need the determinant in order to do that. So, and that will eventually allow us to solve systems of linear equations. That's kind of where we're going. All right, you can pretty much ignore this slide because I'm not going to explain any of it really. But for the record, the determinant of the square matrix is given by this. Is given by that formula. I can just tell you kind of what it is in sort of in human terms. Yeah. Let's go back to this matrix. All right, I forgot to do this the first hour. I promised myself not to do this, is to walk beyond out of the camera range. So I'm going to stand right here and try to do this without going to the board. What you do is you take some entry out of the first column. You just pick an entry. And then take one out of the second column, take another entry that's not in the same row as the first column. And then you take an entry out of the third column that's not in the same row as either of the two rows you picked before. And so on, and you do that, and you'll pick n entries, one for each row. One in each column, such that no two entries are from the same row. So in fact, you will have also one entry from each row, exactly one entry from each row, because you have n entries, and none of them are the same row. There are lots of different ways of doing that, right? You could you can pick all the entries on the diagonal, for example. That would satisfy that, right? Or you could pick A21 and A12, and then the rest of them from A33 on, you can pick on the diagonal. Okay, there are lots of ways of doing this. So do this in all possible ways. And when you get this, when you do this, you get n entries. Multiply them all together. And now what you do is you add up all the results. So add up all the possibilities of doing. So do this in all possible ways. For each way you do this, multiply the entries that you get. And now you add up all of these results. That's not quite it, because some of the ways you're going to do this, you're actually going to subtract instead of add. And what you subtract, how you know when to add an entry and subtract it, is what this Levi-Chibisot symbol doing. It's basically you add it for even permutations and you subtract it for odd permutations, and that's what I don't have time to explain. So, but that's basically that's one way of computing the determinant, and somehow that's how the determinant is defined. Now, this seems completely arbitrary and stupid and complicated, but it actually really is a good natural way of coming up with a scalar value associated with a square matrix, and it's very useful. And we are not going to use this way to calculate determinants. We'll have different ways of doing it. So that's what we're going to talk about now for the next, probably till the next break, is computing determinants. All right. So if we apply the formula without going into any detail about whether you add or subtract, for a 2x2 matrix, it's fairly easy. There are only two possible ways of coming up with these combinations, right? You can take the main diagonal, 5 and 2, or you could take the off-diagonal entries, 1 and 3. So 5 times 2 is 10. 1 times 3 is 3. And the rule is, from before, is actually you take the main diagonal and you add it, and the off-diagonal product you subtract. So the main diagonal product gives you 10. You subtract the off-diagonal product. That gives you minus 3. So the total is 7. So for 2x2 matrices, this is very easy to do. And this is worth memorizing. Really is worth memorizing because you're going to be using this a lot. So anytime you want to take the determinant of a 2x2 matrix, you multiply the main diagonal entries, and then you subtract the product of the off-diagonal entries. And that's it. Okay, so it's particularly simple for 2x2. I guess there's a simple one for, you could have a 1x1 matrix, right? If you have a 1x1 matrix, this is probably the simplest case. The determinant of this is just 3. You just take that entry, okay? And you don't negate it. So 1x1 is probably easier. But 2x2 is the first non-trivial case, the one that's actually you have to do something. All right. So here are the general formula for a 2x2 determinant. You multiply the diagonal entries, A11 times A22, and then you subtract off the product. You multiply the off-diagonal entries, and you subtract that from the product of the main diagonal entries. A21 and A12. Even some animation to help you out. So it still looks kind of unnatural, but it has some nice properties. And here's one nice property of determinants. The determinant of a product is the product of the determinants. So if I multiply two square matrices, A and B, with the same order, I'm going to get a square matrix of the same dimensions. If I take its determinant, that's the same. I'm going to get the same thing as if I took the determinant of A and took the determinant of B separately and multiplied those two scalars together. So on the right, I'm multiplying two scalars, the determinant of A times the determinant of B. On the left, I'm multiplying two matrices and then taking the determinant of the matrix product. It turns out you get the same scalar, regardless of how you do this. So that's one nice property. So if you happen to already know the determinant of A and the determinant of B, you don't have to you don't have to do any new calculation really to get that. You just multiply those two together. So here's an example. So the determinant of A is 7. That's from the previous slide, actually. The determinant of B, well, let's do it. You multiply the diagonal entries, you get negative 3. And then you subtract the off-diagonal entries, so you subtract a negative 8. So subtracting a negative 8 is the same thing as adding 8. So it's going to be negative 3 plus 8. That's going to be 5. So if we multiply these two matrices, and be using the two-fingered rule. So 5 times 1 is 5, and 3 times 4 is 12, that gives us 17, and so forth for the other 3 entries. Now, if we take the determinant of this, it's going to be 17 times negative 8 minus negative 19 times 9. And if you do all the math there, you're going to get 35, which is the same number that you get if you just multiply 7 times 5. So you'll actually get the same number. So given the kind of obscure definition of determinant, it's kind of almost magic that this works. Submatrices. So our next job is to figure out how to compute a 3 by 3 determinant. So we know how to do 2 by 2s. That's easy, and you should memorize it. So we're going to spend time learning how to do a 3 by 3 determinant. So to do that properly, we need to introduce some new concepts. So a submatrix, if I take a square matrix, say 3 by 3, you could do this with any, actually you could do this with any matrix. A submatrix is obtained by deleting any number of rows and or columns and then just closing up the gaps. So for example, I might delete the first column and second row of this matrix. And if I do that, I get a submatrix. I close up, I get 2, 3, 8, 9, that's what's left, and I just close up the gaps and I get a 2 by 2 matrix like this. Just keep them in the same arrangement. So a submatrix is any matrix that you can get this way by deleting some number of rows and or columns and then closing up the gaps. In particular, notice here I just deleted 1 row and 1 column. Okay. In that case, if I started with a 3 by 3, I'm going to get a 2 by 2. And if I had a 10 by 10, I'm going to get a 9 by 9 if I do that. All right. So let A be a square matrix and let little a be one of its entries. The minor of little a and big A is the determinant of the submatrix you get by deleting the row and column containing A. So if A here is, hold on a second. I want to get that out of the way if I can. I can't. How do I? No, I don't want to do that. I made it worse. See if the mouse works.
Just be able to drag that thing. Just drag it.
Oh, okay. Yeah, I can drag with the mouse. I can't drag with the stylus, but I can drag with the mouse. There we go. Do the cha-cha. Okay. All right. So let's take the minor of 4. There's only one 4 in here, and that's in the second row, first column. There it is. So it's the 2, 1 entry of A. So I delete its row and its column, like I did on the previous slide, and I get 2, 3, 8, 9 as a submatrix. Take its determinant. I get minus 6. So 2 times 9 is 18, and I subtract off 8 times 3, which is 24. That gives me a negative 6. Negative 6 is the minor of 4 in A. So take an entry of a matrix, remove its column and its row, take the determinant of the submatrix that results. In this case, it will be 2 by 2, which we already know how to do. Okay. So that gives us a minus 6. Now, the trouble is, you can't just say the minor of 4 in A because 4 might occur in more than one place. And that's ambiguous, doesn't tell you which row and column to remove. So instead, we often discuss the ij minor. It's the minor of the entry at row I and column j. So that tells you immediately what column and row to remove. So the 2 first minor of A, that's the second row, first column, right? Row always comes first. Second row, first column, that minor is negative 6 because that's the determinant of what you get when you remove those 2 of that row and that column. Okay, so that's a minor.
The way to think about that, sir, is almost a reference to a submatrix, submatrices, two submatrices. Like you would get the submatrices 2, 3, 8, 9, which is submatrices, by taking the minor of A sub 2, 1.
I guess so, but that's almost like the reverse. So first you get the submatrix, and then you take its determinant, and that gives you the minor.
Sorry, I'll stop talking.
Everybody good?
That's great.
Thank you.
You get there?
Ooh, it's all just like. Didn't see that.
Sorry. That's I won't move around. Okay. All right. Next up, it's just a little distance to go from minors to cofactors. So what is a cofactor? Well, let's let A be a square matrix, same old square matrix we've been dealing with. The ijth cofactor of A, and it's denoted like this: capital A, and now I and J are in the superscript. First, you take the ijth minor of A, and you multiply it by -1 to the power I plus J. So, you take a minor, but then you multiply it by this. Well, -1 to the I plus J, it's either going to be +1 or -1, right? Because you're taking -1 and you're multiplying it by itself, I plus J, many times. So, if you just have -1, it's going to be -1. But if you take -1 times -1, you get +1. And if you take -1 times -1 times -1, you're going to get -1 again. So you just alternate between +1 and -1 as you multiply -1 by itself more and more times. In fact, you're going to get +1 if I plus J is even. Right? So -1 to the power of 2 is a +1. And then if I plus J is odd, you're going to get -1. So, in the last example, the cofactor is, well, you take the minor, which is -6, and you multiply that by -1 to the 2 plus 1. Well, that's -1 to the third, and 3 is odd, so that gives you a -1. So it's -1 times -6, +6. So the two first cofactor of A is +6. All right, good. So notice that it's useful. So this number, -1 to the ij, it only depends on I and j. So it's the same regardless of what the matrix values are. And it only depends on the position. So here, I and j are both 1, so I plus j is even. It's 2, so it's a +1. Here, I is 1 and j is 2, so I plus j is odd. That's a -1. And every time I go down 1 or over 1, I'm incrementing one of I and j and not the other, so I'm going from even to odd. So if I do that, I start with plus, and I always alternate going either down or to the right. I get this checkerboard pattern. So I just alternate pluses and minuses on every row and on every column. Okay? So that tells you, this checkerboard pattern tells you how to go from the minors to the cofactors. You take the minor, look where that minor is, look where that entry was that you've got the minor of, look at the checkerboard, and if it's plus, the minor and the cofactor are equal. And if it's minus, the cofactor is the negation of the minor. It's minus the minor. All right. So that's really the only difference between minors and cofactors. You take the minor and you apply either plus or minus according to where it is. Checkerboard pattern. All right. So, if we go back to our formula for computing the determinant of a third-order square matrix, that's the 3 by 3 matrix. If we apply the definition, which I promise not to explain, and I drive it all out, it turns out there are 6 possible ways of choosing an entry from every row and every column, multiplying them up. And 3 of them you add together, and the other 3 you subtract. And this is what I didn't explain. That's how you do it. Now you can regroup this expression here. So this is an expression, an expanded expression for the determinant of an arbitrary 3x3 matrix. You can group this up into 2x2 determinants. And here's what it is. You take A11 times the first times the 1, minor. Subtract A12 times the 1, 2 minor. Plus A13 times the 1, 3 minor. So here's what you're doing. You're taking each entry in, say, row number 1. So we're looking at the first row of the matrix. Take each entry of the row, multiply it by its minor, its corresponding minor, the determinant of the matrix you get by removing that row and that column, and then do that for each entry in the first row, and add them up, except that you alternately add and subtract. Add, subtract. Well, that subtraction you can think of as coming from the checkerboard. So actually what you're really doing is you're adding up each entry times its cofactor. And you're adding those all up. So this is A11 times its cofactor plus A12 times its cofactor, which is minus this determinant because of the checkerboard, plus A13 times its cofactor, which is plus because of the checkerboard. So this is actually, I'm doing this on the first row. Okay, so I'm taking A11, A12, and A13, multiplying each entry by its cofactor and adding up all the results. That gives you the determinant of A. And here's the interesting part. Row 1 was completely arbitrary. You don't have to use row 1. You could use any row. You always get the same answer. You always get the same number. So it's the sum of all the A's in some row I times the corresponding cofactor for that entry. You multiply the entry times its cofactor, add them all up for any row, and you'll always get the same answer. That will be the determinant of A. So Aij is the cofactor, and it's found by multiplying the minor by this either plus or minus 1. If A is 3 by 3, then the minors are going to be 2 by 2 determinants, which we already know how to do. Now, this approach works generally. So what that means is, if A is 10 by 10, you get the determinant of A in the same fashion. You can take any row of A, take each entry times its cofactor, which is going to be a 9 by 9 determinant, plus or minus according to the checkerboard pattern. Okay? So in order to compute a 10 by 10 determinant, you have to know how to compute 9 by 9 determinants. Okay? Well, we already know how to compute 2 by 2 determinants, so now we can compute a 3 by 3 determinant. But if we know how to compute 3 by 3 determinants, now we use the same formula. We can now compute a 4 by 4 determinant using the exact same 3, because now the cofactors are going to be 3 by 3 determinants for a 4 by 4 matrix. So the idea is, if you know how to compute determinants for a square matrix of order n, this tells you how to compute it for a square matrix of order n plus 1. You get the next higher up. Okay. So we're going to go, this will take us from 2 by 2 determinants to 3 by 3 determinants. And we'll stop there, because there's actually better ways to do it. And once you get beyond 3 by 3, there are actually more efficient ways of computing determinants, which we'll also talk about. All right.
Dr.
Yes.
If you use the second row of a 3 by 3 matrix to compute the addition and subtraction signs would reverse. Is that right?
That's correct. So yeah, good point. So if you use a second row, look at the checkerboard. So the second row of the checkerboard starts with a minus sign. So you'd have the minus sign first. So it'd be minus, plus, minus. Yes, absolutely correct. Good. Yeah, so the plus, minus, plus only works for odd rows. The even rows, you start with a minus sign. Yes, thank you.
So you could use just a diagonal and always have it plus.
Yeah. No, you can't. Nice try. Good guess. But no, you can't. You have to go across one row. Yeah, you're not allowed to mix and match rows. Okay, you have to choose one row and stick with it. Yeah.
How about for columns?
What about columns? Yeah. Yes. You can also do this with columns. So you could pick a column and go down, pick any column, go down that column, multiply each entry by its cofactor, add up the results, you get the same answer, you get the determinant. Yeah. So this also works for columns as well. This is actually useful because you get the same answer no matter which row or which column you use. But some columns, if you use some row or some column, you might find are going to be easier than others. Like the best thing you should do is look for a row or column that has lots of zeros in it, because then you don't you're going to multiply. You don't have to compute the cofactors because you know you're multiplying them by zero, so they're going to go away. So this is useful so you can pick a row or column that's going to be easy for you to do. Okay. All right. Well.